So without further ado, I'll carry on basically talking about what we think is the motivation for thinking in terms of real power computing and why we need this. And then I'll be talking about different aspects of real power computing, what are the different types of the real power computing, and that will, I think, tie in very nicely with the next talk, which is what Jeff is going to lead. And we'll also talk about some really initial investigational results. This is not really conclusive of the entire paradigm that we ambitiously want to develop. And then we'll talk about some of the ongoing research and challenges and conclusions as well. Now, starting with something which is a bit of a hope and a bit of a challenge, and really the setting the challenges and opportunities for the technology, different kind of technologies. As you can see, one of the trendsetter and also the champion of all had been the disk capacity over the years since 1990s, right? So it has been increasing drastically, and the kind of increase that you can see from 1990s until now is in the order of millions. Obviously, this dates back to the idea of magnetic disks. Well, some of you will argue that magnetic disks will cease to exist at some point of time. But again, depending on the type of computing that you're talking about, this will possibly remain to be used in many more computing systems. Right, CPU speed. Unfortunately, it did pick up in the beginning very well, but it didn't pick up as good as the disk capacity. Everybody knows why, because dark silicon, power densities and everything came into play, and we started the tradition of doing parallel computing instead of doing a single CPU, high-speed computing. So power density together with the dark silicon effects and other things have actually really inhibited the progress of CPU speed. RAM capacity has also increased substantially over the years, but that again is something tied up with the CPU as well. You couldn't just put in lots of RAMs just because you want to make your processor faster. There is also a caveat for putting lots of RAM into your system as well. So again, the wireless transfer speed, thanks to multiple input and multiple output technologies, we have now seen drastic development in this space as well. The speed has increased almost by almost 2 orders of magnitude or so. That is brilliant. But one little thing that is staying at the bottom is really the battery technology. 1799, Alessandro Volta invented batteries. It was ginormous in its sizes and everything else, and it is believed to be the biggest innovation for mobile devices ever in the history of mankind. So obviously, the electronics came a lot later, until around 1980s and 1990s, and we started having new technologies of batteries, new kinds of batteries with the innovation of new form factors and new chemicals and other things coming in. And that gave us a little bit of age, but really, what's falling behind is the battery technology. Everybody has really gone way above the roof. So what the key highlight here is that the battery waste disposal and maintenance has been always a factor that is inhibiting many applications, many fire and forget applications, for example. Now, we did manage very well, didn't we? We managed very well in terms of living with these limited capacity batteries. How did we manage? We sourced internally or externally these 3 different things in really a kind of a nutshell. We sourced batteries from battery developers. We sourced software from brilliant software developers, and also we sourced hardware from the hardware team. What we did is we integrated them in one place with a kind of user-facing kind of environment, where the user was able to communicate with the application software, and the application software was able to interact with the system software, and obviously everything running on the hardware systems as well. Now, the job of really maintaining energy efficiency, the trend-setting curve of energy efficiency with this limited battery technology has been really low-power design systems. And the low-power design, if I name all of them, obviously there will be so many of them. I just happen to mention only 4 of them. These are the major innovations in the space of low-power design. The first one, of course, the first and foremost one is the dynamic voltage and frequency scaling. This, I believe, is the most significant innovation since the low-power design has come into place. Then the power getting circuits and systems, which is where ARM has a lot of contribution over the years, especially deeply embedded power gating. in the circuits and systems, how to disable parts of your circuit when you don't need it, or how to possibly reduce the power substantially at a in a rather sort of a deep sleep mode if you don't really need it. Then, of course, we have parallelization and design and runtime task mapping and resource allocation. This is something we have been working, we have made significant progress in with the likes of Prime project, for example, and some of the other projects as well. So what we do is we have multiple applications coming up with different kinds of workloads, and what we essentially try to do is we try to match up the communication between the application and the hardware by smart design time and runtime policies, essentially managing parallelization, resource allocation, smart controls and monitors, dynamic feedback kind of fashion, and so on. And of course, there's also a community which is strongly propagating for mixed signal design for energy efficient computing. So we have analog ICs, digital ICs interfaced by a common mixed signal interfaces. So far, so good. We have done very well in terms of energy efficient computing using low power design. But can we remove the batteries? Yes, we can. I mean, this is something we have been working on for good long 2 decades now. People have been working on replacing the replacement battery replacement technologies in the likes of, let's say, energy scavenging technologies. So these are just some of the examples of energy scavenging technologies. There you see the RF energy harvesting with the obviously the person attributed to it is Nikola Tesla, famously known for also the Tesla car and the innovation behind it as well. Solar energy harvesting. Obviously, this is something that depends on the area. It's very important that you give it some sort of area, because the efficiency is something that you cannot really hugely benefit upon, because this is something that is already happening in the order of 20 to 30%. Vibration energy harvesting. This is something this particular image I've stolen from Steve Beebe. I hope he doesn't mind if he's around. This is, again, very much a subject specific. If you attach it to a human, you're only going to get, in the order of a few microwatts to maybe a few milliwatts. But if you subject it to, for example, be attached to a machine constantly vibrating, this will have a lot more power scavenged out of it. Then we have some newest trends of really doing thermal energy harvesting, or even implantable harvesting. You kind of implant some piezoelectronic devices, piezoelectric devices alongside the, for example, implanted, for example, pumps, hard pumps and stuff like that. So you can scavenge energy from that as well. You also have multimodal energy scavenging, where you can have thermal and solar energy scavenged at the same time. You can pretty much fix that on top of your hand. And again, depending on the environment and also the subject, you could actually scavenge almost several milliwatts of energy. So one of the things that is really common, apart from the RF energy scavenging here, is that all of them come with two domains of variations. One of that is called the temporal variation. You couldn't really tell, obviously with some level of predictability, you couldn't really tell for certain that, okay, this is going to be the energy scavenged at this particular time, because everything is dependent upon time, weather, and many other uncontrollable factors that you have. And also, there is another factor, which is the difference between the minimum VDD and maximum VDD is likely to be much, much higher than the existing embedded battery system technologies. And these are things that kind of tell you that, okay, I'm going to have an input stream of power coming in, and then I'm going to have a bit of computing done on the other side. Do I need some kind of impedance matching between them? Do I need to make sure that the compute that I control is a function of the incoming power or not? That leads to the kind of nice statement by someone called Oliver Heaviside. We'll talk about this one a little bit later, but let's think of this fact that we have lots of technologies enabled by batteryless systems, really, essentially batteryless systems. And that will, I'm talking about in the order of, the devices in the order of trillions. So trillions of ubiquitous systems are about to happen anytime soon, and this is something we cannot really control. It is going to happen. Industry is leading to that end. But the questions are, how can we make these devices? Because there are so many trillions of them, and they are batteryless as well. So how can we make them autonomous? How can we make sure that they go out there in the environment and start operating on their own? They don't have to be looked into their recharging, maintainability, or all those different kinds of issues at all. This is a big issue the industry is facing right now, academic researchers are also facing at the moment. How can we make the electronic systems, self-powered electronic systems, completely autonomous? And of course, there is this big question about productivity. I'm sure some of my friends from ARM, they are already, especially from the verification team, they always have their deadlines. And these deadlines are pretty, intense because, there is a lot of verification, validation that you need to do for each and every product that comes across. So in order for us to really increase the productivity to that scale of trillions, we need to do something different. We probably need to go from this particular step to the other, which is the step-changing technology. Now, a gentleman, I'm going to talk about a gentleman who probably had a part of the answers that we are going to going to answer today, and I think we are inspired by some of his visions. He is not very well known, unfortunately, but some of you will probably know. Oliver Heaviside was based in the Northeast region. He spent most of his lifetime working for Northern Telegraph and also Bell Technologies. He was a self-taught electrical engineer and mathematician and also physicist, self-claimed physicist as well. What he was really known, during his time, he was not really known for being an extraordinary scientist. He was really known for this: arrogant, rebellious, unreligious, and extremely talented. He actually, at one point of time, he actually refused to take the Royal Society recognition. He just said there was an postal request for him to come and receive the Royal Society award, but he said, no, I don't want the award, take it back. So he was really that arrogant. But he said something extraordinary, which is this. In Maxwell's theory, especially when you're setting up a communication system, the magnetic forces are to be set up by the current in the wire, right? So we see that we want to set up a certain magnetic force, so that eventually leads to the idea of having to set up a current in the wire. Now, what he said is remarkable. He said, can we reverse this? That means I want to have a definite amount of current in my wire, and then I want to find out somewhat definite amount of magnetic force that I can modulate, right? So can you see what he's basically suggesting is that, having some sort of definitive answer in terms of what you can control and what you cannot control. Current is something we can control. Magnetic forces can obviously be, a function of distance and many other things, that you can imagine. But what he's basically saying is that it's the definite amount of battery to the wire and the rate of transmission that we have to find out of it. So if I take the inspiration from Oliver Heaviside, this is what we are saying. Power, incoming power from the batteryless devices, self-powered devices, is the first citizen. So why not control the computation around it using the first citizen as the controller, which is the power? That's why we call it real power. Power is the most real thing in self-powered systems. It's coming as in, it's coming every single time. Every single time you have a different amount of power coming in. So you have to compute and you have to control your power, computation, using the first citizen, which is the power. Now, with that view, can you see there are two really remarkable things that will come into your imagination, which is, first of all, the autonomy. If I take away the battery completely, what we have is a system where I don't have to worry about recharging. I don't have to worry about maintenance. So that's great. So every 2 years or every 5 years, I have to go back and recharge my battery or maybe replace the battery. That is now gone. Now, if I introduce the concept of self-adaptivity, what it means is that I will be able to live with whatever power I scavenge, and I will still be able to deliver the amount of computation that I need for that particular given application. And that is, of course, not the current trend, the state-of-the-art computing systems. What that basically means is that if you have less power, can we still deliver the similar amount of computation capability, maybe at a lower quality? Can we do that? And of course, the other thing that you have to do is that if there is no power, you still have to make sure that your system retains the computation state at all times. There will be times when the system will be lacking power or losing power completely. So that will eventually mean that your system, for the autonomy to be achieved, you need to make sure that the system is featured with the dynamic retention capability at all time. And one of the recent trends of really using the ubiquitous systems is that we have fire and forget systems. So that means you just deploy a computing system, and you deploy somewhere else, and you completely forget about that once and for all, because you can commission them in millions and millions of the same product. Now, productivity is obviously that does not come with the autonomy. It's a different thing altogether. In order to increase the productivity to the level of trillions, what you need to do is you need to make sure that the power delivery and the energy energy transparency or power performance models, and also the hardware and software, all of them will have to be packed in the same piece. So they have to be integrally tested, verified, and validated as in one set of hardware and software altogether. And this is not easy either. So I'm going to so basically go through the different components of real power computing as we see it. So if you have a sort of unknown power supply, for example, some scavenging sources. So what you need, as I said, we need some capability of doing elastic computing or power proportional computing. So depending on the different levels of power, we have to make sure that we still compete with the same capability. And of course, we need on-chip power delivery and sensing and control technologies. And that will only be possible. The only way we can make the battery, the self-powered systems to be governing the compute possible is by having some kind of impedance matching kind of models, which is what I call as power energy transparency. Can I make sure that the incoming power and also the computation power, they're very well known ahead of time, somewhat to some extent, so that I can match between what's coming in and what it is to go out, right? And that will lead me to do something very smart, which is called power compute co-design. Eventually, using software, for example, you can mention what quality you require, what energy you are after, and what is it you want to deliver in terms of performance. And with that around that, you will be providing with some sort of a co-design, which is co-design basically meaning that you will be scheduling power for individual computation requirements, right? And obviously, you can't do away with the only design time optimizations. You also need runtime support, a support system which is built around making sure that the system is survivable at all times. And that's why you need runtime adaptation. Can we make sure that the quality that we are providing right now is maximized in the next time around with the same kind of power capability or power budget? And with that, what you will be doing, you'll be running a set of communication tasks or I/O tasks, hardware tasks, and software tasks, because you're based on the principle of real power computing, right? So basically, the existing technologies already have this, but what we're proposing is that a set of new research domains, really, where you can actually make sure that the system is autonomous by its own characteristics. Right, just some typical examples. Again, in traditional systems, if you were to take out the battery and replace the battery by, let's say, some energy scavenging sources, so what you would do is you would have some sort of power. You normally have some sort of performance requirement, okay? And what you want to do is you want to meet the performance requirement and also at the same time minimize the power as much as possible. Now, if I did replace the battery by simply an energy scavenging source, that chances are there will be times when there will be no power at all. And that would mean that the system will go completely, system will completely lose the computation forever. So you have to really restart your, whatever it is you are doing, again, to start doing some sort of meaningful computation. That's not nice. And also, at the same time, there is no notion of controlling incoming power to the computation capability, right? Now, with the real power computing, what we're saying is that whatever it is, the power is whatever power is coming in, we will have to have the capability of ensuring that we have some strict power, energy, and quality requirements, together with possibly some performance requirements as well. And then what we will do is we will elastically control the computation quality based on the incoming power or energy and performance. So can you see on the real power computing side, what we have is some power budget which is being formulated in real time. And based around it, we are making sure that we are meeting that power budget at all times, and eventually making sure that we are also retaining the computation and computing on a continuous basis. Right. I'll be brave here right now, so basically just using some terminologies. So if you think of a system where you have only this energy scavenging source and no storage at all, you're basically left with something called hard real power computing. So you have to live with whatever it is, the power that you have scavenged for that particular system. So that is pretty challenging, because that will need a very good transparency both from the load side and also from the source side to make sure that you can always formulate power budgets accordingly, right? On the other hand, if you have, let's say, a bit of storage with the energy scavenging in the form of, let's say, supercaps, you can then introduce something like soft real power computing, which basically means that, yes, I can formulate the power budget, but the power budget can be occasionally violated because I have some stored energy in my system. Okay, I'm aware that the time is nearly running out, so I'll probably skip some of these things. So this is something I wanted to show before I finish. So what we did is we did some experiments based around power adaptive computation. So what we did is in an OpenCL environment, we designed 4 different versions of a multiplier based on some of the existing works that we do. The first one is obviously the traditional Wallace tree multiplier, followed by some different approximate versions of the same multiplier with increasing approximation. That means as you go from the left-hand side to the right-hand side, you have the approximation is significantly higher. Obviously, if you use the original multiplier, you have a certain level of power, and as you keep on increasing the approximation, you save the power significantly. But at the same time, that has a cost of having errors introduced. Mean squared error is really close to 0 over here, and of course here the mean squared error will be increasing over time. So what we did is we emulated in an environment where we were able to simulate the power source variations, and we also formulated some power budgets based around what's coming in, reducing the losses, of course. And then we found out using machine learning some policies of scheduling power, scheduling the multipliers depending on the incoming power that is coming in. And also the aim is to basically optimize the quality while also meeting the power budget at all times, right? And this is what we got. This is a fantastic result. I think this is something which is still work in progress. What it basically means is that, as you can see, as the power goes down, obviously you're having to cope with this one by using more approximate version of the multiplier. But as the power goes down as low as 0, so then the system goes to a mode called retention mode, so that it doesn't do any computation at all. So it's really adapting to the power at all times. So incoming power is whatever incoming power it is coming in, is adapting to the incoming power. Okay, so this is again an initiative. I'm sorry, I think we have because of the right. So this is an initiative that where we're actually forming a team, active team, with a program grant initiative led by Alex, and I'm sure the likes of Jeff, Kirsten, and some of these other academics that we have from around the UK, they will also be talking about these things at some point. So Newcastle University is leading this one. Obviously, we have ARM, Southampton, Bristol, Imperial College London, Intel, and Intel AMD, and some of the other players as well. We're still hoping that some of us can also join in. If you're interested to talk about these concepts, I'm happy to talk about it at some point. Yeah, thank you very much, and apologies.